From the wind-whipped, glacier-chewed fastness of the far north to the countless sun-soaked coral atolls of the Pacific Ocean and all areas and climes in between, man has conquered the Earth's surface. Geographically, he has crossed all frontiers but one, straight up, possibly the most dangerous of all frontiers crossed thus far. This search into the reaches of the Earth's atmosphere and beyond, plus a day-by-day advancement in the technology of the Air Force missiles, is the story of the Air Force Missile Development Center. One of the 12 centers of the Air Research and Development Command, Holloman is located in the Tularosa Basin in southern New Mexico and is some 10 miles from the city of Alamogordo. Holloman is bordered on the east by the 9,000-foot Sacramento Mountains and on the west by the 7,000-foot San Andreas Mountains. Down through the centuries, many things have happened in this basin that are duly noted on the pages of history. Eons ago, a deposit of pure white gypsum sand, 200 square miles of it, was built up by the whims of wind and rain. This is White Sands National Monument. Across the basin, land of the Apaches, in the 16th century, conquistadores marched, seeking new lands, new fortunes, new frontiers for the King of Spain. Centuries later, a new era was born with the first atomic detonation on the face of the Earth, Trinity, in 1945. Soon thereafter, the mighty V-2s captured in Germany thrust their sleek noses into the upper atmosphere. In this basin, man rode down a track at the fastest ground speed ever attained by any human on Earth. In the thin upper air over this desert floor, rockets carried mice in place of men to learn the secrets of space, and here they floated weightlessly. This 100 by 40 mile test range, perhaps the most instrumented and surveyed piece of real estate in the United States, is the Holloman-White Sands Integrated Range. The Army and Navy hold most of their firings on the southern portion of the range, while the Air Force concentrates most of its activities on the northern two-thirds. To piece together the day-by-day testing of both Air Force and upper air research missiles, to fully understand the behavior, to record the full scope of the operation and efficiency of missiles at Holloman, the shops, the laboratories, the measurement systems, and the control stations of Holloman stand ready. This center is devoted to a full-time qualitative collection and analysis of data for missile contractors. This is the Holloman mission, service to contractors. At this very moment, in a hangar near the flight line, Falcon missiles are being loaded into the armament bays of an F-102 fighter interceptor. The Falcons are air-to-air missiles developed for interceptor missions to knock enemy aircraft from the sky. The objective of this firing, to study the reactions on the F-102 launch aircraft and to record the results of firing the Falcons into a B-17 target drone. The target drone is ready for takeoff as a man on the ground controls it remotely with his beeper box. Overhead, the mother plane sweeps in, and control of the drone passes from the man on the ground to the controller in the mother plane. The pigeon is in the air. Comes now the hunter with his falcon. Now, all attention is focused on the control center, King 1. This is a building of radars, of computers, of plotting tables. Here, too, the contractor waits impatiently as the last few minutes tick off. He is but one of the many Air Force contractors who use the data collecting facilities at Holloman to record the behavior and eventually prove out their missiles. Captain, could you take just a moment to explain the layout of this mission?
Yes. This is a controlled scientific experiment Instruments up and down the range are zeroed in to record this run. And essentially, our job is to put the run in the best location for such instrumentation. King 1 to F102, 1795, continue on present course. Time is X minus 5 minutes, all stations. All aircraft are flying a racetrack pattern on the range. They are tracked by radar, and slant range and course information is set into computers. The path of the aircraft over the ground is then displayed on this plotting board. This particular board shows the location of the target aircraft and the launch aircraft. King 1 to all stations. This is a hot run, 1795, vector starboard 260 degrees.
Bully Papa, start your left turn now.
$17.95, this is King 1. Steer starboard, 10 degrees. Make it hard. Will you give me an altitude check?
Up 500 feet.
Roger. 1795, this is King 1. Climb 500 feet. Check optics and telemetering. $17.95, this is King 1. You are clear to lock up and fly the dot.
Fly the dot. At the precise instant the dot rests inside the tiny white ring, electronic equipment in the F-102 takes over, holds the plane on its course, and fires the Falcons into the B-17 drone. Another of the missiles being tested today is the Matador. This is a surface-to-surface tactical guided missile capable of being catapulted from a zero-length launcher. This missile has been under development for some time, but even though this missile has operational status, it is still under development to improve its accuracy. Today's test is another in a series of checkouts of a new type of guidance system. Checking this system calls for major use of elaborate instrumentation techniques. Optical and electronic systems will be in full operation today to record the speed, flight characteristics, and behavior of the Matador as it moves through the sky over the Holloman Range. The missile is ready for launch. A solid propellant booster will blast it into the air. Then its jet engine takes over once the booster cuts out and falls to Earth. The test range over which the Matador flies today is much more than just an expanse of barren desert. Scattered at strategic locations over the basin floor and on the surrounding mountains are the integrated instruments that track and record the behavior of missiles during flight. The complexity of the instrumentation setup is such that only an impression can be given of the numerous optical and electronic measurement systems. Under optical systems are to be found the Ascania stations. This is a German-developed instrument using two telescopes, one for azimuth and the other for elevation, to track the missile and record on film position and trajectory information. Mobile units of servo tracking cameras using a modified B-29 turret mounting high-speed cameras with long focal length lenses provide time history records and target altitude and miss distance data. Another optical instrument is the Intercept Ground Optical Recorder, known as IGOR. This unit uses a reflecting telescope in conjunction with a motion picture camera to secure records of performance, missile altitude, aspect, and angle of attack. In addition, there are various types of high-speed and ribbon frame cameras on the range to provide detailed histories of ground launchings in the early stages and to provide accurate velocity and acceleration data. For airborne coverage, a number of separate but synchronized 16-millimeter cameras are mounted in pods on target drones. The cameras are equipped with wide-angle or bug-eye lenses which overlap to form a sphere of vision about the drone. If the drone target is destroyed, a timing mechanism ejects the pod, a parachute opens, and the system floats to Earth for recovery. Electronic systems are also important test tools. These radars and attendant plotting boards are used in instrumentation for tracking, range safety, and in determining impact points. One electronic instrument is called the velocimeter, a unit used on the range to gather velocity data during stages of missile launching up to about 4 minutes. Two other electronic systems, too incredibly complicated to describe, are the MIRAN and DOVAP networks. MIRAN consists of a master and 2 or more slave stations out on the range. These stations collect and record signals from the missile in flight and by a system of triangulation pinpoint the missile's precise position in the air. DOVAP, on the other hand, consists of 2 transmitter stations, 1 recorder station, and 11 receiver stations. These stations record, through variations in radio frequencies, information on velocity, acceleration, and position. When any missile flies at Holloman, it is constantly watched, checked, and recorded from the instant it leaves the ground to the end of its test run. Turrets and antennas swing with it, recording every yard of its progress. Out in the middle of the basin floor, several miles from Holloman, stands a rocky mound known as Tula Peak. Within the buildings atop this mound are the recorders of the telemetry system, another way of providing contractors with data on how their missile behaved. Even now, helix antennas are focused on the rascal high above. Although it cannot be shown in detail for security reasons, it is visible to the eye as a contrail high over the Holloman range. Below, in the recording room. Sir, could you talk to us for a moment, please?
Yes, sir.
What we would like is a quick trip through your installation.
Yes, sir. Right now we're receiving data from Bell's Rascal in flight. The equipment along the wall forms the ground receiving portion of an FM-FM telemetry system. The equipment receives the transmitted signal from the airborne transmitter located in the missile. This information is recorded on this oscillograph and on magnetic tape. The oscillograph is usually considered the primary recording medium. Information is presented in the form of galvanometer traces on photographic paper. We can also record any or all of the signals received on magnetic tape. These tapes can be played back at any time to make any number of oscillograph records. Other recorders can be used to monitor from 1 to 4 continuous channels and provide a quick picture of missile behavior during flight.
Records like these collected at Tula Peak are sent directly to data reduction for processing. This machine, called a telereader, is a direct reading device to take measurements from oscilloscope tracings. Information collected optically is also processed, for example, Ascania film. On this viewer, azimuth and elevation readings are interpreted and punched on IBM cards. The data contained on the IBM cards set in motion elaborate computing equipment. The cards are sorted, and through a series of steps too complex to follow in detail, information is processed and presented in tabular lists and in graphic form to the contractor. This is another way in which the Air Force, through facilities at Holloman, provides assistance to contractors in the development and testing of missiles. The processed data is passed on in the form requested to the contractor. Not all of the testing done at Holloman is in the air. The captive missile test range is a high-speed ground track, a precisely aligned roadbed 35,000 feet long. Since the flight testing of missiles in the early stages is a complex and costly method of gaining data, captive testing makes it cheaper and quicker to do the preliminary work on the ground. The high-speed sled is also used to study the effects of mechanical forces on living tissue. Colonel John P. Stapp, head of the Aeromedical Field Laboratory at Holloman, is in charge of these studies. Colonel Stapp, would you tell us of some of the phases of aviation medicine you and your staff are investigating here at Holloman?
Certainly. While here at the center, you have seen a number of missiles, vehicles that have eliminated the pilot. But for all this, we are not in the strict push-button age. Manned aircraft are still our first line of defense. Aircraft that in many cases equal or exceed the speeds of pilotless missiles. When a man rides in a pressurized cabin, that cabin can blow out. A man hits his parachute. Wind blasts him with the force of 10 cyclones. He dives straight down and becomes weightless. He banks sharply in a high-speed turn and becomes a lead statue. Man does not become a problem child until the plane he is flying fails. So far, man is still a finer control system than man himself can devise. Okay. Space biology begins with problems of flight above 50,000 feet. We need to know so much more about the problems of flight in the upper atmosphere and even outer space. As a result, our work is cut out for us, as we utilize the many tools here to meet the many challenges in aviation medicine today.
In 1954, Colonel Stapp rode this sled down the track at Holloman at 632 miles per hour. He endured a wind pressure of 1,100 pounds per square foot and stopped with a peak force of 35 times his own weight. Earlier, the colonel spoke of some of the problems encountered. Let's see how some of them are solved. Inside one of the buildings at Holloman is the high altitude chamber, or to be precise, the environmental simulator. The simulator can and does create the exact conditions encountered by man at extreme altitudes. By placing man within the chamber and simulating the desired altitude, it is possible to subject him to the pressure, temperature, and even humidity experienced in the upper atmosphere. Within such a chamber, it is possible for the Air Force to observe and record the responses of man and his equipment in the prelude to actual high-altitude flight. However, it is not possible to understand all facets of high-altitude flight through ground testing such as this. There comes a time when man and his instruments must go aloft and see for himself. Man has flown experimental aircraft at altitudes above 100,000 feet, yet only long enough to give the pilot a fleeting moment at that height on any one flight. For careful, prolonged observation, balloon travel is more practical. For this purpose, a pressurized gondola or capsule capable of carrying a human observer to the outer limits of the Earth's atmosphere is to be used. On the inside, the capsule is cramped and rather uncomfortable, but does have windows for the pilot to observe the view. It can hold adequate supplies of food and water, and is fully equipped with delicate instrumentation to measure and record conditions of wind, temperature, cosmic rays, and whatever else Air Force scientists need to explore and study. However, the most important instrument of all is the pilot himself. For no mechanical gadget yet invented can tell exactly how it feels to a living human to hover on the very threshold of space. There are biological questions to examine, such as the effect, if any, of cosmic rays on the human body. And there are psychological questions to be answered. How will the human mind and spirit react to the sensation of drifting in cramped quarters, completely alone, 20 miles above the Earth? Although the basic research for this high-altitude ascent was conducted by the Holloman Aeromedical Field Laboratory, the actual launching took place on the plains of Minnesota, where atmospheric conditions are particularly favorable. The balloon is made of a nearly transparent plastic material. It measures 280 feet long and has a capacity for 2 million cubic feet of helium gas. The balloon climbs at the rate of about 1,000 feet per minute. At the desired altitude, 96,000 feet, the sky coloring changes to a dark blue-black. The horizon is over 400 miles away and 18 miles down. The descent is accomplished by simply allowing gas to escape through a valve in the top of the balloon. In this instance, the balloon and capsule missed the trees and landed in a small brook. Here, at the end of its flight, the capsule with its human cargo is met by crews that have followed every minute of its flight. The capsule is set upright, opened, and the pilot emerges unscathed and unharmed. 18 miles may be high up for man, but not for some of his instruments. For still higher altitudes, we go back to Holloman, to the Aerobee Tower, the rocket tower. Except for a few degrees of tilt, it points straight up to the last frontier. Universities and research institutes from all over the nation use the Aerobee rocket to further Air Force knowledge of the upper atmosphere. Even now, men from one of the research institutes work on the nose cone as they prepare an experiment to study the air glow phenomenon. This atmospheric light is due to a small amount of atomic sodium, which through direct reaction with solar energy during daylight and through photochemical processes at night produce a yellow sodium light. The Aerobee will place a trail of sodium vapor along its trajectory over an altitude range of 40 to 70 miles. The observations will provide information on the presence and activity of atomic sodium high in the Earth's atmosphere. At the launch site, the Aerobee launching crew finishes transfer of red fuming nitric acid and aniline, and then it is 19.5 minutes after sunset.
This is Aerobee command to all stations. The time is now X minus 15 seconds. 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Even as the Aerobee races to altitude, other events take place. Due east of the Aerobee launching site, high atop the 9,000-foot Sacramento Mountains, are the buildings of Sacramento Peak Observatory. This is one of the 12 laboratories of the Air Force Cambridge Research Center and is dedicated to the study of the upper atmosphere and outer space. Within this building at Sacramento Peak, a man watches intently as his recorders measure and document the phenomenon associated with the air glow studies. It was for this man that the Aerobee was sent some 70 miles into the sky over the Tularosa Basin. Actually, the air glow study is but a small portion of the total activity at Sacramento Peak. The Air Force is also deeply involved in various phases of solar research. Another aspect of upper air research is the study of the behavior of meteors. A special instrument records on photographic plates the activity of those particles of matter that flash through our solar systems and bombard our atmosphere. Outside, in a black box, known of course as the coffin, a man lies prone and looks up into the darkness for the telltale flashes of light caused by the meteors. From here, he remotely controls the telescope inside and records a story which could have a vital bearing on future upper air travel. It is here on Sacramento Peak that the Air Force has erected the world's largest optical instrument, a coronagraph, for observing the behavior of the sun. The sun's behavior actually has a direct bearing on some of the delicate modern devices here on Earth. Disturbances such as these can produce complete or partial blackouts of radio communications for several days. They can also produce variations in the strength and direction of the Earth's magnetic field, resulting in navigational errors. From studying the sun high on a mountain to diagnosing the complex operation of missile components, the Air Force is interested in all things pertaining to the air and to that empty space beyond the air. This kind of testing at Holloman is an ever-changing picture. Missiles, contractors, and engineers may come and go. Scientists from universities and men of the Air Force may be here today and gone tomorrow. But the shops, the instruments, the communications, the computers, and Holloman will remain. In the sandy southwest basin, rimmed by high mountains, the history of the Air Force's determination to advance in missile technology becomes part of the record every hour, every day. In the words of General Nathan F. Twining, Chairman of the Joint Chiefs of Staff, the frontier which we must defend today lies neither to the east nor west, but directly above us. This is the frontier of the future.